Okay, hello everyone. I'm Junxue from SysTech, and today I'll give a presentation about our work, prompting large language models for training-free non-intrusive load monitoring. Okay, so here's the plan for the next 60 minutes. First, I'll give a bit of background and motivation. Then I'll walk you through our framework and the prompt design. After that, we'll look at the experiments and the key insights we learned. And finally, I'll give a short conclusion and take your questions. Okay, let's see the background first. So, non-intrusive load monitoring, or NIM, tries to figure out how much power each appliance uses using only the aggregate power at the meter. So instead of putting sensors on every device, you just measure at a single point. And an algorithm, NIM algorithm, can give you appliance level insights. I think that's nice because it's low cost and easy to deploy. But it's a really hard problem. So in recent years, most strong NIM systems use deep learning. Deep learning works well on the benchmarks, yeah? But in practical, we see three main problems. So the first one is the data dependency. So you need a lot of high quality labeled data to train the model. So that's so expensive, and it's really hard. And the second one is poor generalization. A model trained in one house usually doesn't transfer nicely to another house or another country. You need recollecting the data and retraining the model again and again. And the second one is the totally black box. Users don't know, why the predictions are made. Yeah. So at the same time, the large language models are getting really strong. So they come with larger pre-trained knowledge. They generalize surprisingly well, and they can understand and generate the natural language. So that brings us to three research questions and drive this work. The first one is effectiveness. So can large language models actually do NIM through a prompt-based in-context learning? And the research question two is the generalization. So if we only change the prompt, can they generalize across different houses and different regions? And the last one is explainability. So can they give us human readable explanation for their decisions so the process becomes less black box? Yes. So to explore these three questions, we build a framework and we call it the large language model for NIM. Yeah. So the idea is quite simple. So on the left, we have raw aggregate power data from the sensors, and we convert that into prompts. So it includes appliance information, the examples, the context, and so on. And we send this prompt to a large language model. And the model outputs the appliance states and the explanations for the decisions. So you can see the model here is fixed. We don't train anything. Yeah. So the performance then depends heavily on how we design the prompt. So we finally settled our four key pieces. The first one is the base prompt. You can see the roles, the task, and the output format requirement. Yeah. The second one is knowledge injection. So for each appliance, we provide things like the power range, the duration, the usage pattern, and we give one short example. So the input, the output can be better. Yeah. So and the contextual information. Yeah. So we can also feed in the previous Windows prediction states as context. So make the current decision smoother. Yeah. So before we jump into answering the research questions, we first need to check the check whether this framework even works. Yeah. So we start with preliminary experiments. Let me see. We use the red and the Ukidel as the two standard famous public NEOM data set. So we use the precision, recall, and F1 score as the matrix. That's the most common. Yeah. We begin with one-day case studies to understand the behavior. So then later move to the large-scale evaluation across lot of data time points. Yeah. So let's see the first. First we update the prompt components. Yeah. We start with a simple base prompt and gradually add the one-shot example, the knowledge injection, the time steps, and the contextual information. So we found that adding one-shot example helps a bit, and adding domain knowledge helps more. The biggest performance boost is the context. Yeah, that's the most important information. And we finally found that the basic prompt plus the contextual information plus the one-shot example and plus the domain knowledge creates the optimal prompt. So we finally use it. Yeah. Then we zoom in on the knowledge injection itself. We test three types of knowledge: the power range, the duration, typical duration, and usage pattern. So the observations are the power range is the most crucial. Yeah. So if we remove it, the F1 score drops a lot. It's really mean signal. Yeah. And the pattern and duration are complementary, and all three together are optimal. So we finally use these three. Yeah. Next, we do a sensitivity analysis. We vary window size, how many time steps we include in one API call. Yeah, and the second is contextual alerts. It means how many parse states we parse as context. Yeah, contextual information. So for window size, we found that bigger is not always better. So larger models can benefit from longer window size, but smaller models actually perform worse when the window size is too long. Yeah, and for the context alerts, there is a sweet spot. A short context helps stability, but a very long history may add noise and confuse the model. Yes. So in other words, for AM-based NEOM, you really need to contain model size, the window size, and the contextual alerts. Yes. And we also look at the output of stability. Yeah. This is very practical. When you push a small model with a large window, two things often happen. The first is the number of predictions doesn't match the input length. We call it misaligned. So the second one is JSON format is simply broken. Yeah. So that's malformed. That's very bad. Yeah. So larger models are much more robust under the same settings. They produce few formatting errors and more consistent output. Okay, based on these observations and some extra case studies, you can see it in the paper. We made two design choice for the large scale experiments. The first one is we choose the DeepSeek V3 for its top performance and the lightweight GPT 4.1 mini for its efficiency in the later large scale experiments. And the second one, we don't use reasoning models, and we're focusing on state detection. Not the power estimation. Yeah. Okay, now with the optimal prompt settings, and we can finally run the large-scale experiments on the RAD and UKDL dataset to directly answer the the 3 research questions. So the first one, the effectiveness, the first message is yes, the large language models do have basic NEOM capability. Yeah. So with our framework and optimized prompts, large language models you can see the features can correctly capture the sharp specs from the devices like the microwave and the kettle, and it can also capture the complex pattern like the dishwasher and the washing machine. Yeah. So that's right. Yeah. But when we compare to the specialized deep learning models, like the sequence to sequence and sequence to point, we can see clearly, the accuracy gap. On both RAD and UKDL, the overall F1 score of large language models is significantly lower than the deep learning baselines. Yeah. Okay, that's the research question 1. And the research question 2, generalization. So here, large language models show a very interesting advantage. So the first one is across houses. Yeah. So on RAD, we extract appliance knowledge from the house 2 and 3, for the prompt. Yeah. And then apply the model to the house 1. We test on the house 1. So it never see it before. Yeah. So with just the same prompt, it still gives reasonable disaggregation result. Yeah. And across regions, so we then move to the UKDL in the UK. So where the appliance set is difficult, is different. It has the kettle. Yeah. We only update the appliance description in the prompt, the knowledge injection. And the large language model can still identify the kettle's usage pattern. Yeah. It's very simple. Large language models behave as kind of the plug and play. Yeah. Okay, the third question, the explainability. So it's true that large language models are also black box, inside the technique, but they have one unique advantage, so they can speak natural language. So we ask the model not only to output the applied states, but also give a short explanation for each decision. Yeah, you can see in the left, it can matching the microwave's profile and not matching the the fragile. Yeah, so all these explanations are human readable and verifiable. Yeah. So even when the prediction is wrong, the text tells us what the model was thinking. Yeah. So we can refine the prompt accordingly. So that's the explainability. Okay, let me end with the main takeaways. So large language models offer a training-free approach to NEOM with powerful generalization and explainability, but currently trained these benefits for lower accuracy compared to the specialized deep learning models. Yeah. So in our view, their current value is less about replacing NEOM models and more about serving as a flexible, interpretable component in future areas like smart home agents. Yeah, I think. Okay, that's all for today, and thank you very much for your attention. So I'm ready to have any questions. And after the conference, if you still have any questions, you can send an email to me.